Also start the recording.
No. So, good evening, everyone. Today's lecture will be about me showing how to solve the notebook, and followed by quantum entanglement and quantum teleportation. So, let me share my screen first. So I have already given two lab notebooks. Please download it if you haven't. These are present in here. First, I will go through the A2 IPNV Open Notebook A2. I'm showing how to do this. Please bear with me. So this is very simple notebook, uh, very beginning, just for the beginners. First of all, let me select my kernel, and that will be in the previous session you learned about how to select the kernel, how to download Miniconda. So I have selected the CWQ, coding with Qiskit. Now in this notebook, first you can read these following steps. Let me not going through the steps, let me directly tell you to first run this cell. These are already installed in my laptop, so I don't have to worry about. You can install it, that will be not an issue. And these are the import sections. We will run it too. Next up, we are building a quantum circuit, which is already imported here, of quantum circuit of which consists of two qubits, which is of two qubits and has two classical register and two quantum register. Let me increase the size. Yeah, the first two are the two quantum registers, and second one are the two classical registers. Let me run this. You will get a clear picture of this. So two quantum registers, as I said, Q0 and Q1, and a classical registers of also 2-bit. Classical register is for measuring. I will come to it. Next up, we will be adding a X gate. X gate is for flipping on qubit at 0th position. The 0 means at 0th position. This one. Just run it. Yeah, and for showing the result, we are using a matplotlib library to draw the quantum circuit. You can see the X gate is added in the 0th qubit at position 0, I mean the Q0. Next up, we have Hadamard gate at this Q1. Yep, we got it. Next up, we will be measuring. Measuring means we just observe it on the classical register. This is in the part of quantum, and this is in the part of classical. We will be measuring these two. Now, okay, we will run this one. It says, okay, so this is a task where we have to do. Your task is add 4 total gates into your quantum circuit, mix them between two. You can either use NOT gate or okay. Add total 4 gates. Either we can use NOT gate or Hadamard gate. So let's do this. This is our quantum circuit of 2 qubits. Is always 2 qubits and having 2 quantum registers. So let's add some gates here. Let's add X gate in the 0th qubit. Again, Hadamard gate at again 0th qubit. Again the X gate at the first qubit. We will see what it see the result of the following. Yep. So you can clearly see we have X gate and this two X gate on the sorry this and this two on the 0th qubit, and this one on the first qubit. First is H gate, so H gate is before X gate. We have applied X gate before H. That's the order. Next up we have simulators. So as we are not working on quantum computers, real quantum computers, so we will have our own machine. We have our own machines that does the similar kind of work like the quantum computer. We had already imported this AER simulator before, and we will using this as our backend. Next.
Hi, Debajyoti, can you little explain this simulation? I'm little bit.
This simulator is like we cannot do the like, how can I explain this? We cannot do this thing in our own machine. Like this is a quantum computing.
Yeah, that means in classical machine.
We are doing this classical. So to simulate this, I mean to replicate these things, we are using this simulator. Actually, what happens is nothing classical happens. Each gate represents a matrix. So we are adding, we are XORing, we are doing the inner product of this matrix, and after all we get a result here. Okay, so
without simulator it is possible or not possible?
Can you repeat?
Without simulator it is possible to get this?
No. Absolutely not. We are we are replicating the quantum environment in our local machine. Are you getting it?
So I have a question that. So every time we need a simulator?
Yes, absolutely. We will need every time we will need a simulator to view these things. Like, what is this measuring? What is this actually measuring? What will the output be? Output here will be. After this, initially what Q0 and Q1 is storing at this point, Q0 and Q1 storing both are storing 0 ket. In this line, in this circuit, if we see, after crossing this X gate, the 0 turns into 1, ket 1. Okay.
Yeah.
Now this is the Hadamard gate. What happens in Hadamard gate? It puts into a superposition state. So that will be 0 and 1 both simultaneously will be existing.
Yes.
When we will be measuring, either we will get 0 or we will get 1.
Yes.
We will run it 1,000 times, 10,000 times to get the probability. We will get the probability, whether how many times 0 is occurring, how many times 1 is occurring. That's how this thing is done.
That means you tell that that's 1,000 times and 10,000. This simulation done through this simulator.
To this one, yeah. By default, I think it's 1024. 1024 times this thing is running to get the appropriate result.
We can change default means without simulator.
No. Without simulator. I haven't. Without simulator, I mean, here I will compile this thing. To
yes.
Here I will compile this thing and I can run it. I can add shorts. Sorry, the spelling is shorts. Shorts is equal to 1,000 times. This means that it will run 1,000 times and will give me the result according to it. 1,000 times this circuit will be running. 1,000 times, out of 1,000 times, how many zero is occurring, how many ones are occurring, that we will get as a result. I will definitely show you how this thing is done.
Okay, thank you.
Yeah. Where I was? So in this, let me explain it. Yeah, you can speak up if you are raising hand. I don't see. Okay. Anyone raised hand or something? No. sorry for that. Now what we are doing is this sampler consists of this backend, and we are running it 1024 times to get the result, and we are getting the count. Okay, I can show it like this, that I already told you that what we will get is 0 1 0 1, and here also the initial qubit was 0. After crossing Hadamard gate we have 1 and 0 simultaneously. Now we have the X gate. When we will be having 1, then it will convert it to 0. When we will be having 0 here, it will convert it to 1. Okay, now you can see this. I think it's running 1000 times. We have 2 qubits, so 2 to the power 2, 4 possible states, 0 1 0 0 0 1 1 0 and 1 1. So 0 1 occurring 235 times, 1 1 occurring 247 times, and this way. If I run it again, this value will change. You can see this value will change every time I will run again. Also one thing, the Qiskit notation, if you see this one, I can't zoom it right now. No, I can't zoom it. If you see this one is actually Q0. This Q0 is actually this one, and the first one is actually Q1. The Qiskit notation is reversed, so keep this in mind. Yeah, we are running it by default. We are running it 1024 times so that we can have randomness in the result. It's already written here. Now we have to make a Bell state. For Bell state, you will be learning more in the next stuff of quantum teleportation and entanglement. So let me do as they say. The image will the circuit will look like this kind of. Let me quickly do this. So what will happen again? We have two quantum registers, Q0 and Q1. So apply Q0 to applies Q0 to 0th qubit. So QC dot X to 0. Put 0 into superposition. What does that mean? QC dot H, apply Hadamard gate to the 0th qubit and entangle together. Entangling, how can we do? By the C0 gate. We'll do this by QC dot C0 CX gate. C0 is CX gate. X not gate is denoted by X. Controlled not gate is denoted by C1 CX, and we'll have the controlled here and the target here. Yeah, you see the similar, I get the similar result. So you know about the QC, controlled X gate, where this is the controlled qubit and this is the target qubit. Whenever the controlled qubit is 1, it flips the target qubit. It means that consider the initially Q0 was 0. After crossing X, it will be 1. Here it will be 1 in this. This is a where, and we have the gates here. First 0, crossing X will be 1. Now crossing Hadamard gate will give us 0 and 1 together. That will be existing simultaneously. So when Q0 will be 0, the controlled we have this controlled NOT gate. Whenever Q0 is 0, the value in Q1 will not change. Whenever the value in Q0 is 1, the qubit, the value in Q1 will change. So Q1 is by default having 0. So when this will give out, this will result in 0, Hadamard will give 0, then it will result in 0 0. When Hadamard will have 1, it will give result 1 and 1, as it is by default 0. 1 flips this bit and we get 1. So zeros, so we will get either one of the two result, 0 0 and 0 1. With we will get both with some probability, like we can run it after that. Okay, so let me run this. Okay, let me explain what will be the probable outcome here. H get and C not get. So H, I am having 0 ket here, ket 0 here. After crossing H, I will have 1 and 0 together. When I will have 0 here, this will not change, so it will give me 0 0 as a result. When Hadamard will give 1, then 1 1. So what will be the result after measuring? It will be either 0 0 or 0 1. Let me quickly code this thing. This is QCEX2 dot H at 0, QC dot CX 0, 1. Target is 1, control is 0, control is 0, target is 1. Let me run this. Yeah, we get the similar result. Okay, next up we have this on how to run this on real hardware. There's nothing to you have to paste your token here. How to get your token is simply search IBM Quantum, or I have given you the link. You can sign in as you wish, but I already have signed in with IBM ID. You can go with Google or something. So let me quickly grab this one. I have this my token. I think I shouldn't do this, as you can see below here. The wait time is around 9 hours and queue position is 77. So by entering this small code, you will be polluting this thing. So it's recommended to use your own machine rather than to use the IBM Quantum platform. So yeah, you can.
How do you get the token? Sorry, Debajyoti? How do you get the token? Just can you see?
Yeah, I got the token from here.
How?
Okay, go to IBM. Is this quick?
That's cool.
You see this?
Okay.
You can click on it.
Yes.
You will land here. You will land here. You can go with any of the option.
Yes.
And fill up the name, whatever they will ask.
Yeah. I already filled and.
Yeah. So you will, after that you will land here.
Yes.
API token.
Yes.
Copy it.
Then, yeah.
Copy it. And you can paste it here.
Okay.
And run all the cells to directly. You can see. You will be seeing your job here. You will see your quantum that code you have put on the real hardware here only.
The dashboard, okay? The dashboard.
This is a dashboard. Is it clear by all of you?
One second, just in the dashboard. You can click the dashboard. Dashboard, there is some status. Yes, not showing in dashboard. There was some. Okay, fine. Thank you.
Okay.
Thank you.
So, okay, I am showing you how to do the graded notebooks. This will be really quick. There's nothing to do. You can see there's only 2 exercises here. You will be given this notebook, which is fairly hard, a bit difficult. You can ask anytime to any of any of our organizer for help. You can solve it after the session on quantum entanglement and teleportation. You will be able to solve it. So I have shared this one too, the QFF graded notebook one. You can download it, and again we will be we will be running these cells, and I will be showing this really quick how things will happen.
So you run this code in your local,
Yes, I'm running this everything in your local machine.
or it is not impacting your laptop? Means what is the how much configuration required for this run this kind of code in a local?
How much configuration?
There is a chance, right? There is important documents in our locals. So if I run this kind of code, quantum computing codes or quantum bits code, so they might be impacting. They might impacting our local usage, right? So sometimes if you run the code, normal machine learning
Yeah.
models or any kind of neural network model, you
No,
run.
no, that's this Qiskit is not that heavy. As we are using very low qubits, like I think we are able to use only 25 qubits, I think so far, or at max 100 qubits we can use. This is very less.
So from 100 qubits, how many resources they allocated for your computer? From your computer resource, how many resources are allocated for this 25 or 100 qubits?
That I haven't checked, but I haven't faced any problems till yet.
Debajyoti, actually, during I have when we have in some implementing some ciphers, we have done some little bit complicated quantum circuits. Mainly, I prefer on cloud, but that time IBM lab was live. Right now, it is not live. Other
They have
cloud
shut it
environments
down
are there,
actually.
but
So,
still,
like
machine.
if I use, like I have a Azure services. So what kind of Azure services we required for this?
No, actually, for this, whatever actually IBM, what number of qubits provided by IBM, actually, why we use IBM or Qiskit, not others I can talk, but mainly the advantage of IBM is that the number of qubits. It provides the more number of qubits, and also 8 GB was there in case of cloud, and here also in our machine 8 GB is there, and that is enough for running this. But even if we have 16 GB RAM, but if we want to run some complicated circuit with some prober cells, say, even if for 5 qubits, I could not able to run within 3-4 hours it will take. Even sometimes I could not run even for even 5 qubits when it is running simultaneously. But yeah, complete circuit more than 300 qubits I have implemented. Not just the implementation. Qubits are there, not the simultaneous I'm talking about. So actual qubits means that whenever simultaneously all this parallel processing is there, so that time even to recover 5 or not 5, I could not able to, or I do not know anyone has been able to recover except Caesarean cipher like this. So this more than 5 qubits, but 3-4 qubits actually that take too much hours. Actually, it can be done within your 8 GB RAM, but still.
So means
And
it
that
will take like
cost calculation is there. So that is actually always not parallelly going with this your machine, because some noise also imparted in case of quantum. Even if we are not producing in hardware, I'm talking about simulation.
Oh, yeah.
Either
I'm
may-
also talking about the simulation. Yes, I'm also talking about the simulation part. Like when I'm simulating the code or we done the model, so how much time it will take for the local?
No,
like,
actually depends.
That
It
depends,
depends.
actually.
I say depends based on your circuit complexity. Okay. As in case of algorithm, circuit we know time complexity, space complexity, right? Here also
Yeah.
circuit depth is there. Yeah, circuit depth is there. So that parameters are there here also.
Circuit depth
So
is
based
number
on
of gates you have in a single.
number of gates there
You have
and
a
some
single
other
layer.
parameters there. So the multiplication of both these things are there. So that cost calculation you have to take into account. But you cannot also I did not. If you can see any recent update, you can also post in for our knowledge also. But we have not seen anything that is we can measure. That's like classical. We can say this amount of this number of instructions. So my machine speed is this. So this will take that much time. That we cannot do for quantum simulation. Even if we know how many gates are there, what is the cost, we know the machine speed, but we cannot calibrate this thing, or I have not even seen. So if you see, then any type of research or update anything, you can update. Yeah.
And
Is
if
it
I
clear?
like, if I not run in my local, or I use maybe at some cloud like AWS or Azure, so what kind of services I need to activate for this?
And not much, not much, not much. So I will show you that Google Colab also today, and
Okay.
QBread. Both are preferred by IBM. Those who are scientists, those who are actually doing the research, designing this. When they are producing the talk and their written documents, you can see over internet in their materials shared by them. So they are preparing. That is, since their IBM lab is not live online, I am saying. So they are preparing this Colab or QBread. Also other, but they are preparing mainly these two in order: Colab, Google Colab, or QBread.
Okay. Thank you.
Only.
Yeah, under the hood, we are actually doing the mathematical calculation, the matrix calculation, matrix multiplication actually. So that depends on how much time it take.
Debajyoti, please run which version the others participants
Yeah,
can see.
the
Yes,
version is
you can see
1.2.4.
one. Yeah,
It's
updates.
the latest version, and please use version after 1.0 or higher. Next up, just download it. I have this open here. Let's run it. Fine. Next up, we have the imports. Now, this is this is nothing even. Okay. The task says just to make it a string, anything string. So just to show how the gradder actually works. Yeah, this is the lab grader. We have already installed the lab grader here. Where it was here. Install the lab grader here, through which you can check either you are correct or not. Yeah, we are getting this kind of message. If you are seeing this means that you are successful in figuring out how the grader for this notebook. Next up, we have some errors and the solutions for those errors if you ever encounter this error. Next up says, okay, we have did this in previous A2 notebook. Same. Now 3 observables are given here, and we have to write 3 observables according to this. So let me quickly do this. It says IZ, XX, and XI. IZ. This is IZ, XX, and XI. XI. Run it. This is observables. You can grade it. Yeah, that's correct. Next up, we are using a backend again. Backend's AER simulator as our backend to compile our code and run it locally. And lastly, we will be plotting this in a graph, and at the end we have this histogram. I can show you one more thing for extra. I think this will work. You can do what's like you can measure this and plot this in a histogram. Let me quickly do this. Simulator. Let's take simulator. Just AE. simulator and compiled circuit. I have to import trans file too, and just extra I'm doing import trans file. Sorry. Next we have the job. That will be simulator dot run compiled and the shots. Just take it 1000, I think 1000 yeah, 1000 times this will be running. The results will be shown in job dot results result, and we'll be counting this as well, how many times each Q0 and Q1 appearing. Counts will be result dot get counts. This will be results second here, and the sprint count first. Okay. Okay, let's run more thing. Okay, sorry, I haven't imported the classical registers here. Next up, we will be measuring this on classical register. I haven't even measured this. Classical register is 2. I'm eliminating this. Classical register is 2. Okay, and now I'll be measuring this. UC dot measure all. Now this thing, yep. So 00 occurs 526 times, 11 occurs 474 times. Every time I will run, this will give me the randomness. Again, if I print this in import dot as ELT. Let me plot so 1 2 3, let's go with 3 PLT dot let me show it. Sorry PLT dot what kind of showing counts dot is and count dot values. Counts. No, still not there. I think I have to give the X level and Y level thing. Measurement and Yeah, I'll picture this in a graph. You can see, oh, that's a really great number, 500. So that's all. I will share this, the updated code and everything. So that's all from my end. You will be given this second graded notebook, which we will be able to do after the next next talk on quantum entanglement and teleportation. So, thank you.